So Sayan's background is in civil engineering, but he is interested in efficient seismic acquisition for near-surface characterization. So we put together this so that we can answer the question of how do we best deploy the location of sensors.
Before I'm going to make a quick comment on the recycle reclaim part of it.
Yes.
So my two thoughts on that one is that we have existing projects, right? With an abandoned oil that has reached its end of its life.
Yes.
And so clearly we would like to use that asset further, right?
Yes.
So a natural one would be to make it into CCS project.
Yes.
Then recently there has been discussions about should we do geothermals with CO2, right? And so a further extension of my CCS project could then be to do geothermal.
Yes.
Use the same site kind of internally for many different purposes and repurposes, right?
Yeah.
The same token, all the kind of, there is now, I think, many more interesting land use cases and conflicts coming up with the CCS, I mean, with farming, with solar, wind farms, critical mineral mining, so overall mining on groundwater, right?
Yeah.
And I think there is a big aspect in that in there to help us kind of, how are we going to use this asset or this site in a best way, essentially, for all the stakeholders in there?
Yeah, that's it's a really good question when we put it in the context of a energy mix, right? And multiple, how a piece of land can be used for different purposes, or CO2 for that matter. And that's why, well, I guess later on this afternoon you will hear a talk from our ECE collaborator. What we were trying to do is to put different sources of energy into consideration and run an optimization problem with respect to what is the market, what is the impact, and can we put different weights on different considerations and coming up with an optimal solution. So thank you very much for that comment. Go ahead. This is an optimization problem too.
Yeah, thank you, Alita, for introducing me. So as Alita introduced, I'm Sayan. So yeah, I'm going to talk about this optimal sparse seismic acquisition design using compressive sensing, mostly for near surface acquisition. That's a cool animation of our group logo. Okay, so let's see what is compressive sensing. So this is basically a signal processing technique that we mostly use in our daily life when we save an image in JPEG or other formats, which basically samples the image to reduce the file size. But if we reopen the file, we see a reconstructed image, which very much resembles the original image. But let's see how this sampling happens in this pictorial format. So let's assume this is our original data or original image. And we are using this sampling matrix to sample that image or data. And that gives our sampled data or image. So now compressive sensing is based on that idea that the data or signal has to be sparse in some domain. But often the data is not very sparse in the measurement domain. So we need to take it to some transform domain where it is sparse. And we are using this sparse transform domain operator F here, and that gives us our sparse coefficients. So I forgot to mention what is sparse is. Basically, it's like it should have very few non-zero coefficients. So now let's see why we are interested in compressive sensing for seismic acquisition. So generally, in a very large scale or industrial acquisition, for example, if you're doing a land survey where we use a dense 2D receiver array with maybe tens of thousands of receivers to image or get a 3D image of the subsurface. Or maybe for geological mapping where we are trying to delineate the boundaries or the faults. Or maybe for oil and gas exploration where we have like a very dense receiver array with multiple source locations. Or for example, for a marine acquisition where we are again using a dense receiver grid with progressive source locations. So these are the cases for a large scale acquisition. But talking about small scale acquisition, that's being used these days very much, where we are maybe, for example, for acquiring surface data with multiple channels, where we generally use tens of receivers with very few source locations. Or for example, for monitoring tunneling, as Alita mentioned, where we only considering the tunnel cutter head as our source. Or for carbon sequestration monitoring, or for vertical seismic profiling, where we only have very few source locations on the surface that we are using for monitoring these purposes. So the thing is that for this small scale survey, where we only know that we have very few sources and receivers, how do you want to design that acquisition to decide like where we want to put our receivers or the sources so that we can collect very optimal amount of data? So our research goal is to answer that question. So before that, let's see what are the challenges that we can encounter while doing the sampling. So this is a traditional sampling, which we follow the Nyquist sampling theorem that states to have at least 2 samples per wavelength. And for describing that, I'm using a toy example here where the signal is generated combining 3 frequencies, 3 different frequencies. And when we do a very traditional sampling following the Nyquist sampling theorem, if we get its amplitude spectrum, we can clearly see the 3 frequencies separately that we use to generate the signal. But in case if we do a regular 2-fold undersampling, that introduces this aliasing artifacts in the amplitude spectrum. And if I just blankly present this spectrum, it would be hard to decide which one is the original spectrum and which one is the aliasing artifact. So this is the original signal, which is being masked by the aliasing artifact. So what people generally do, instead of doing a regular undersampling, they do an irregular undersampling, which converts this aliased energy into a background noise. And by doing a thresholding over this spectrum, it helps us to detect that original spectrum over this thresholding limit. Now, the question is, again, for a small scale survey where we have very limited sources and the receivers, do you want to depend on this irregular undersampling to tell us like what are the positions of the sources and receivers should be for the optimal acquisition? Or if we have some access to the subsurface information or some preliminary base data, we still can optimize this acquisition geometry to get an optimal amount of data. So our research focus is to answer that questions, and for this purpose, we are using a 3-layer velocity profile where we have introduced a Q factor to introduce attenuation in the data. And I used the Spectrum 2D software to generate seismic data, dense seismic data DF, which contains 96 receivers with 2-meter receiver spacing. And our objective is to get this sample data DS through our desired sparse sampling vector S. And this red dots denotes basically the locations of the receivers that we are putting inside the whole receiver grid. Now let's see how can we get our desired sampling vector S. For that, we are trying to minimize this objective function J gamma. And we have 4 terms here that I'll go one by one. So the first term, we are trying to fit the data. That's one of our goals. And another goal is to get the sensor sparsity or optimize the sensor sparsity. And the third term, third L2 norm term denotes the model fitting. And the fourth term denotes the model sparsity. And in the previous slide, we have already seen the dense data and the sampling vector. And for our models, so we are using the frequency wave number spectrum as our model domain. And this figure shows the amplitude of the frequency wave number spectrum here. And again, we are using the 2D Fourier transform as our forward operator. And alpha is a scalar that does a trade-off between this data fitting goal and the sensor sparsity. And in this picture, we can see that's the data residual we are trying to minimize by performing while doing the optimization. And finally, this scalars beta and gamma controls the contribution of the model fitting and the model sparsity inside this optimization. And in this figure, I have shown how this model sparsity looks like. So the red color denotes the values of the spectrum that's basically above this value of gamma. So I've taken a gamma of 0.21 here, and the blue color denotes basically all the values that's below the gamma. So I want to mention about something that's like getting this model sparsity is an NP-hard problem. So we can't accurately guess the model sparsity properly. So and also, as the value of the gamma depends on this model sparsity, we have to assume some value of the gamma while we are doing that optimization. And I'll come next how we are doing that operation in our optimization algorithm. So let's see step by step how we do this optimization. So first we have to take an input of our dense data df, and we're also assuming a sampling vector s1, which for our initial sampling vector is basically all ones. And we are assuming some value of gamma to start the optimization. Then we alternate between variables. So what are the variables here? S and M. So first we fix the variable sampling vector S, and we will solve for the model M. And then we'll fix that model M, and then we'll try to solve for the sampling vector S. And by doing this iteratively, we'll ultimately get our optimized model M and sampling vector S for that particular value of the gamma. Now the question is, as I've already said in our previous slide, that getting the value of the gamma, which depends on the model sparsity, is an NP-hard problem. So how do we solve that problem? So we are using a grid search technique to search for that optimal model. And for this, we need to evaluate the reconstructed data that we are obtaining by using this reconstruction algorithm called projection onto convex sets, and for a particular value of S gamma. And that gives us a signal to noise ratio for different values of gamma. We can try to run our iterations on. And finally, taking the maximum value of the signal to noise ratio, we can get like which gamma will take for getting our optimized sampling vector S star here. So now let's see what optimization technique we are using to solve our optimization or objective function. So we are using this nested iterative shrinkage thresholding algorithm. So it's a classic algorithm for solving sparse optimization problem. So first I'll say what is nested optimization here. So as I've already told, we have two variables here that we are trying to solve. One is M and another one is S. So this is a bivariate optimization problem, which makes this objective function non-convex. So we can't use any convex optimization algorithm to solve that. And that's why we do this fixing and solving others, like fix one variable and optimize for the other one. And that for that, we can use any convex optimization algorithm to perform this. So first, let's see how we can solve the model using ISTA. So this equation shows so basically ISTA is an augmented version of the gradient descent algorithm. So this equation, like by using this equation, we can get an updated model using gradient descent, where basically GM is the gradient of the L2 norm terms, eta is our step size, and I is the iteration number. And as I've said, the ISTA is an augmented version of the gradient descent. So what it does, it relaxes this L0 term to L1 norm term and uses this L1 norm term to impart sparsity on our updated model using this thresholding operator tau. And let's see how this operation happens in terms of our results or images. So basically this figure shows how you can update from M0 to M1 using simple gradient descent, which where we are using the gradient of this M0 term here. And after we perform the thresholding, which is basically the augmented portion of ISTA, here we are using a value of the gamma as 0.95. And this is our, again, a thresholding operator where the red color denotes 1 and blue color denotes 0. And that gives us our thresholded updated model here. So now if we change the value of the gamma iteratively, trying to reduce it from 0.95 to a lower value, which basically means we are introducing more information in our model domain. So that basically updates this model, which we can see in this GIF. So now let's see how we can solve our sampling vector S here. So again, we are using ISTA for doing that. And we are thresholding this sensor importance vector here, which is S tilde, using this thresholding operator tau kappa, where kappa is basically the alpha and beta variable, ratio of alpha and beta variable that we have seen previously. And let's see again in terms of results, how this looks like. So this is basically what we call as sample importance vector here. So that's basically denotes the importance of different sensor locations for data reconstruction. So basically the green color denotes all the sensors which has higher importance for data reconstruction, and the other color shows the sensors that has lower importance for data reconstruction. And if we threshold that sampling vector using a thresholding operator tau, where we are basically keeping here the 48 sensors out of the 96 sensors that we started with, that will give us our sparse sensor locations here. So in this figure, I'm showing how this signal to noise ratio varies with the thresholding parameter. And this is a very important figure in terms to describe why do we need to use grid search to get our optimized sampling vector. So this figure, you can see that the signal to noise ratio is not a monotonic variation with the thresholding parameter. It's varying erratically. And that compels us to use the grid search technique to decide on the optimized sampling vector. So to get a better view of like how this affects our variation of the importance or sampling importance vector, we'll take a closer look at two thresholding parameter, which the first one is the 0.125 for which we are getting the highest signal to noise ratio, and which is our basically the optimized thresholding parameter. And this is the corresponding sensor importance vector here. And if we take another thresholding parameter 0.2, which is very closer by to the thresholding operator, the optimized one, we see a very different distribution of the importance of the sensors. Next, let's take a closer look to that optimized sensor locations, which is again a very important picture in terms of the distribution of the sensors. So specifically for surface wave acquisition, we have an idea that the high frequency data mostly remains in the near offset region, where the low frequency data dominates the far offset. And if we see the distribution of the different importance of the higher importance sensors, it's mostly clustered in the near offset region, where it has a very sparse distribution in the far offset. And that basically confirms to the distribution of the different frequency data that we know for a surface wave propagation. And this figure shows how this sensor importance or its importance or what's the distribution of the sensor importance for different sensors. So this also demonstrates the sparsity of higher importance sensors. You can see that the number of high importance sensors are very less, where we have a very high density for low importance sensors. And this red dashboard basically denotes the limit for the 48 sensors that we are choosing out of the 96 sensors. So after seeing all this procedure, how this things goes on, let's see how our proposed method or the results of the proposed method compares with the different random samplings method that is already being used for industry level. So this is our optimal sparse acquisition design that we call as OSAD. And these 5 are the results from different random sampling methods adopted for surface wave acquisition. So there are 2 things that I want to point out here is for this jittered uniform method, we can see a very regular distribution of the far offset traces. And similarly for jittered Bernoulli method, we see a bit lesser regular distribution of the traces. And we'll see the effect of this irregular distribution, the regular distribution of the far offset traces in the coming slides when I show the results. So these are the comparison of the data residual that we obtained by comparing the reconstructed data from different sample data obtained by different of this random sampling methods and our proposed method. And by seeing here, we can see that our proposed method is achieving the highest signal to noise ratio in comparison to the other existing random sampling methods. And there are a few features that I want to point out here. So the first one is for this jitter uniform method, we can see that there is some low velocity artifacts that I have pointed out by these lines. So that's basically getting generated because of this regular distribution of the far offset traces that I have showed in the previous slide. But if we take a look at the jitter Bernoulli method, which has a bit lesser regular distribution for the far offset traces, it doesn't have that much effect of this low velocity artifacts. But this would be more clear when I saw the reconstructed spectra that I obtained from different reconstructed data by different methods. So basically, you will think that they looks very similar. They don't have enough changes in the different reconstructed spectrum. So I would like to point out here what are the differences here. So in this figure, you can see that there are some aliasing artifacts. It might be a bit lower amplitude, but it's getting generated again from the regular distribution of the far offset traces that I showed in the distribution of the sensors. And it's generating this aliasing artifact in the high wave number domain, where it is generating the fundamental and the higher modes in that domain. Similarly, for the jitter Bernoulli method, it has a bit lesser regular distribution, so that's why it generates low amplitude artifacts. But still, by taking a closer look, we can see that here. And finally, though this top three figures doesn't have that much aliasing artifact, or maybe not aliasing artifact, but it has still some background noise in there, which we don't see in our proposed method that much in the high wave number domain. So that kind of demonstrates the effectivity of our proposed acquisition design, where we decide the optimal sensor locations, and that gets our highest signal to noise ratio. And finally, let's see some take-home messages from this presentation. So we provide a framework to determine the optimal sparse sensor acquisition design. And for this purpose, we are utilizing the sparsity of the seismic data in transform domain. For this case, we use the FK domain to determine the sparsity. And we also automatically honors the wave physics. And for this research, we are using surface wave or Rayleigh wave, and we are honoring the distribution of different frequency data for that purpose. And also we can give, or we can evaluate the importance of different sensors that's necessary for data reconstruction. And finally, I have shown that this proposed acquisition design is very much beneficial for designing small scale near surface acquisition, and that the proposed acquisition design can be very much effective for the vertical seismic profiling, or the carbon sequestration monitoring, or for tunneling monitoring. Though this proposed method can be adopted for very large scale seismic acquisition that's mostly prevalent in the industry scale, but as we have seen that for industry scale acquisition, we need a dense receiver grid with multiple source locations, and that may make our the data simulation very costly and time consuming, and that may limit the usage of the proposed method. But maybe for a small scale 2D grid, we can still use this proposed method for designing our acquisition, which still can be very much beneficial. So that's all from my presentation, and I'd be happy to answer questions.
Can you go to slide 6 for a second?